Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
A former colleague of mine, and he will tell us about discrete convex utility functions.
Something like this. Okay, thank you. I'm very glad to be here for several reasons. A, because I like to be in new places and meet new people. And secondly, because it has been my experience that nobody reads my papers, so that at least if I can get some people to listen to what I think I have to say, then at least I get some free advertising space. So the subject that Oded and I thought might interest the audience here deals with the question of quote-unquote construction of concave utility functions on finite sets. So I think it would not be out of order if I start by making sort of a crash course on individual demand theory to explain to you why what concave utility functions are and why are they interesting, before going to the more detailed and more technical question of how to construct them when the data is finite. So the first part would be a crash course to classical individual demand theory. So we start with a consumption set. The individual demand, now I'm going to cheat during all this lecture, as is usually in all such lectures, I'm going to cheat all the time, and many of the words and the sentences that I will make are not entirely accurate and can be interpreted in many different ways, but that's the nature of things. So individual does not necessarily, in economic theory, individual does not necessarily mean a person. Individual can mean you and your husband, let us say, a decision-making, really an economic decision-making unit. So it can be a household, it can be an individual, it can be a company like Microsoft. In some cases, it can be divisions within Microsoft. It can be even countries if you're looking on international trade. But the basic underlying model is always the same. So this individual, and let us consider for simplicity most of the talk only consumption theory. Believe me, there is an analogous theory which has production in it. But there is a consumption set K which is in subset of RL. So the individual components of the vector x, xi means the quantity of the ith commodity or service consumed. So you have a very, well, depending on the model, you have a vector. Every commodity or service are indexed by one of the commodities. And you assume, and now this is an assumption that I'm going to make, that these consumptions are infinitely divisible. So you can ask, why are they infinitely divisible? So if you wish, you can say, well, this is what we do in physics all the time. If you wish, you can say that we are considering not consumption, instantaneous consumption, but consumption stream, how much you consume per week or per month, and then or the rate of consumption, so then it makes more sense to look at this as a real number. At any rate, we are going to not to consider the question of indivisibilities, which is an important question, of course, but not part of this lecture. Now, the individual has a preference relation, preferred or indifferent, on this set K. And there is a huge industry about these preference relations, so I assume that there is symmetry, so X is preferred or indifferent to X. If transitivity, if X is preferred to Y, and Y is preferred to Z, then X is preferred to Z. And completeness, which is now, by the way, even transitivity, those of you who are inclined for psychology know that transitivity does not necessarily hold, But the story that you say A is that people would correct themselves if you present them with proof that they had been intransitive, and B is that you are considering only rational individuals. And a rational individual is somebody who does satisfy all these assumptions. So, so this is the definition.
Do you know any?
Do you really think that Microsoft behaves in irrational ways, or that a company, or even that? Now, irrationality does not mean, even for individuals. Suppose that people purchase drugs and what have you, does not necessarily mean that they are irrational in the sense of economic theory. Rationality means having preference relations. So if you prefer drugs, then you are still rational. Rational means more consistency and having an objective. So we assume completeness, which is a strong assumption, so that every pair can be compared, which is a strong assumption. And we defined also, so this is what I call, and then there is a notion of strict preference. If X is preferred or indifferent to Y, but Y is not preferred or indifferent to X, and you say that X is strictly preferred to Y. And we make once again, a strong mathematical assumption, which is more technical than conceptual. We assume continuity. So in the product set, the set xy such that X is preferred or indifferent to Y is closed. This means that if Xn converges to X, Yn converges to Y, and Xn is as good as Yn, then X is as good as Y. Makes sense. Now come two assumptions which are not innocent, which have economic contents to them, that K is convex, and that the upper level sets are convex. So if both X and Y are as good as Z, then any linear combination is as good as Z. And strict convexity means that they're actually strictly better. That you prefer that this means that the indifference surfaces, the indifference curves, do not contain line segments in them. This is called strict convexity. So this is one side of the story. Then it is very difficult to work. Yeah? I beg your pardon? Well, it comes from the. Well, it does capture in real life that as you will see, there are even stronger assumptions that would capture in real life that the middle somehow captures better qualities than than either extreme. But there are other interpretations as well, as you will see as this lecture unfolds. It is not easy to work with preference orderings. It is easier to work with what is called utility functions. Now, what is a utility function? Utility function is a real valued function on R, sometimes not necessarily real valued, such that, and this is the important thing, that it preserves the ordering. Real numbers have the natural ordering, so X is preferred or indifferent to Y if and only if U of X is greater than or equal to U of Y. And similarly, X is strictly preferred to Y if and only if U of X is strictly better than U of Y. And the idea is that maximizing a function, somehow we feel more at ease with maximizing functions over K than maximizing orders over K. Well, I shouldn't have said this here, but so at least for people in the 19th century, in the 20th century, people thought this way. Now, a convexity, and now I have another answer to what you said. Strict convexity and even stronger conditions are needed if you want that your utility function U will be not only convex, but let us say with the second derivatives different from 0, which in many cases you need, then it would be stronger than the assumption that I made before. So convexity is equivalent to what is called quasi-convexity of U. And however, concave utility functions are widely assumed in applied economics as well in economic theory from the 19th century onwards. So what is important? So first of all, as I will show in a while, convexity of the preference ordering is weaker assumption that the assumption that the utility function is concave. But first let me explain how concavity of the utility function, how does this play a role? It plays a role in many settings. Perhaps the easiest one to understand is with the attitude toward risk. So here you have a picture of two individuals. So risk here does not mean risk in the sense that I drive a car, but risk in the economic sense. So compare the individuals on the upper part and on the lower part. Suppose you have here this axis gives you the wealth. This axis gives you the amount of utility that you derive from this wealth. Now, if you look at the upper individual, this individual, if he gets with probability half 15 and with probability half 5, he will get, according to the von Neumann-Morgenstern utility paradigm, half of U of 5 plus half of U of 15, which is less than U of 10. So this individual would strictly prefer having 10 for sure than having a gamble which has 1/2 5 and 1/2 15. So this individual is risk averse. On the other hand, this individual is risk lover because he prefers the gamble of having 1/2 chance of getting 15 and 1/2 chance of getting 5 than having for sure 10. And so you see that the convexity of the function, not just the preference orderings are the same, they're the monotone. But the question what utility function you have does play a role here in your attitude toward risk. And those who like diminishing marginal utility, you have diminishing marginal utility for the case of the risk aversion. You have increasing marginal utility for the risk lovers. And what I'm not doing, but there is a similar story to be told about production, where the utility function is actually a production function, and there the convexity and the concavity imply increasing or diminishing returns to scale. And once again, this should answer partly your question. So the question of convexity or concavity of a utility function is important. It is not just a question of what the preference ordering is. And now, the following problem arises. Is it true that reference relations are always, which have whether convex preference relations have always concave utility function? And the answer is no. Please look at the figure here. It's a very famous figure. And this shows you a very elementary class of, so the indifference curves are these. They are lines, but they are not parallel to each other. And then you can easily convince yourself that there is no concave function would have this function as its level curves. And here there is a mountaineering argument, which is due to Bob Oman. If this would be a mountain, this is not mountain here. This would be a mountain, then here the ground will rise steeper than here. So that if you take a pole here, and you put the line, then the line will be above the ground, which contradicts the concave utility function, means that this mountain should be convex. So this is probably the simplest example for the phenomenon that you can have convex preference relations and you don't have any concave utility functions representing it. This phenomenon was discovered by De Finetti in 1948-49 in a paper which is written in Italian, so I'm not sure that I understand everything in this paper, but I think I understand this pretty well, except for one key term, which I don't know whether it is an adjective or an adverb, but you know Italian? You know it? Somebody here is an expert on Italian? Yeah. What is minimamente convexa? Does this mean minimally convex or minimal convex? Minimally convex. So this was my conjecture all along, that it is minimally convex. But, well, not all along, but not all along, sorry. In the first paper I wrote about it, I wrote minimal convex. But then I read this once again, I decided it must be minimally convex. Well, actually, I was wrong. Now, this is not strictly convex, but you can easily modify, Fenchel modified it if you can see what you have upstairs. This one is x2 divided by 1 minus x1. This one upstairs is x1 minus x1 to the 4 over 1. And you get strict convexity, and still you have no concave function represented. This is called the problem of concavifiability. And the problem of concavifiability has been discussed in the literature by several people. And in the continuous case has been more or less, there are, if in the situation that I discovered, if K is a convex subset of Rn, there are necessary and sufficient conditions for the existence of a concave utility function representing your setup. And let me, perhaps before I go into these, let me show you one more application of having a concave utility function. If you look at this picture here, it is well known that even if everything around is differentiable and analytic and what have you, still the demand functions can have singularities. However, if the underlying, so this is a demand function, this is the price of commodity 1, this is the demand for commodity 5. The commodity demanded is the one which will be the bundle, in this case, the two-dimensional vector x1, x2 will be the one which will maximize the utility, subject to you being able to afford it. So it turns out that if the utility function is concave, then the only possible singularity is like this. You cannot have any singularity of this type. Whereas if the preference relation is such that it's not representable by means of a concave utility function, you can have many, many other types of singularities. So that so the question whether or not the preference relation is such that it admits a concave utility function is relevant. It's not just something that De Finetti thought about and then some mathematicians who wanted to advance in life wrote papers about, but that it is natural in the sense that it does have economic implications, does have behavioral implications. So, and one of the ways to analyze the question of concavifiability, of having concave utility functions, is, let me just make a two-sentence survey of something which would take 2 or 3 hours to explain. And it is really that if the convexity of a function really can be looked upon by 3 different ways. You can have this as a zeroth order condition. So this is order, and this is the number of points. Now, convexity or concavity of a function can be regarded as a 0-order function, the value of the function relating to 3 different points, A, B, and some point in between. Then you can look at it as a question of monotonicity of the first derivative, or generalized monotonicity or monotone cyclicity for subgradients or what have you. So this would be, you compare derivatives at two different points. Or you can look at condition on the second derivative, or in the several variables second matrix of Hessian matrix for 1 point. So you see that the number, this is a constant all the time, which equals 3, the sum of these columns here. However, there is a strange duality here. The zeroth order condition is very easy to explain geometrically, very difficult to compute. The second order condition is rather easy to compute, very difficult to interpret geometrically. And the first order condition is sort of in between. So let me explain the zeroth order condition. Here you have the zeroth order condition, only you don't realize it. So suppose, let us look at this as if these are the level curves. And I want to construct a mountain, a convex mountain, so that these are its level curves, okay? So what would I do? One possibility would be the following. P0 will be at height 0. Then P1, the indifference curve going through P1, will be at height 1. And then P2 will be on the maximum height, which will still make the mountain convex. Okay? Because if P2 would be very close at a height which is very low to P1, clearly this is convex. But I can raise it. So I raise it until I hit the place where it is barely makes it. And then I continue until I get to Pn. And then I renormalize so that Pn will be at height 1. Now, if I take the limit as this becomes dense, then a necessary and sufficient condition for having a concave utility function will be that this mountain that you get at the limit will be between 0 and 1 as long as you are between the maximum and the minimum in the preference ordering. And the height of this will give you a concave utility function, actually what we call least concave minimamenta convexa utility function for this preference ordering. So if those of you who like to see a formula can see this formula and convince themselves that the formula is not at least superficial. Yeah?
I understand that when you're taking the limit, something will fail.
Yes, the thing that will fail is that, okay, the thing that will fail is the following. Suppose that the maximum here and the minimum is here. When you take the limit, this might happen. Because the limit will be always convex, because the limit of convex bodies is always a convex body. But what will fail is that a non-maximal point will still, the thing will go up. You see, this will be, okay? And when at a non-maximal point you get 1, then this means that there is no concave utility function which we represent the same.
Can the limit also be discontinuous at the left?
Okay, it can. Okay, it can. It depends whether you are on a closed set or on an open set. So there are certain technicalities here that I have to explain. But under normal circumstances, let us ignore them. If you have a preference ordering which is nice on a compact convex set, then this won't happen. But theoretically, it might. Theoretically, it might. If it is extendable, then it won't happen. So if some of you likes to see a formula and to believe me that the formula has become not very illuminating, so here you have a formula. There is, I forgot to, there is, you can, for these three points conditions, you see that you get alpha P1, P2 will be the supremum of the ratios of these. So this is essentially a geometric thing. And if you take these alphas, you can juggle them, and you get an explicit quote-unquote formula for the concave utility function. This, what you have here, is actually what you get if you do what I said geometrically, which is this what you get. So the supremum of this should be less than 1, and you get a least concave utility function if you compute this supremum. Not very illuminating. On the other hand, for the third order case, you get a formula which you can write, but it is difficult to interpret geometrically. All right. So now I forgot to say that part of what so up to now that's the background to convince you that the desire to construct concave utility function is not something out of the thin air, but it is a meaningful enterprise. Now, let me quote from a paper written by Richter and Wong. And so this is quotation. This is not my text. So we should understand what basic properties of preference are implied by concavity of utility functions. K provided complete answer for continuous preference defined on in infinite convex sets. We means here Richter and Wong, can always work with an answer for preference defined on finite sets. Now, why on finite sets? We want to provide an empirical test for existence of concave utility functions. And of course, in real world, our data are typically finite. More fundamentally, to really understand economic issues, it helps to understand their meaning in a context that we have some hope of grasping fully. So this was Richter and Wong decided that they are not satisfied with the constructions that I showed you, outlined to you here, because everything there is at least continuous, if not differentiable. And real life, we always have only finitely many points of data points, and you compute functions usually, if I'm not talking about symbolic computations, you compute values of functions at finitely many points. So they ask the following question: how would you characterize a preference ordering, a convex preference ordering on a finite set, not infinite convex set, but a finite set, such a way that you will be able to construct a concave utility function on this finite set representing this order. So you have to define first what is a concave utility function. This is not very difficult, but let me first give their condition and their theorem. So they have L-dimensional space. And for all n, which is less than or equal to L plus 1, for all distinct x, y1 up to yn in K, and for all real numbers, lambda 1 up to lambda n, positive, such that if the summation of lambda I is equal to 1 and x is this sum, so that x is actually a convex combination, a genuine convex combination, non-trivial convex combination of these points, then there are two possibilities. Either x is indifferent to all of these yi's, or if it is not indifferent to all of them, then it must be strictly preferred to at least one of them. This is a convexity assumption. This is a finite convexity assumption. So this is not, this was where other people, I should not say made an error, but other people thought that looking at finite set, you ask, is there an infinite, is the ordering induced by an order on the convex hull? This is a different condition. This is a condition which is purely finite, and the check is, you can check it by finitely many operations. And then the theorem of Richter and Wong is the following. Let K be a finite set. A weak preference satisfies this condition G. If and only if there is a concave function defined over all of RL, truth of the matter is that it can be defined on a finite set only, and then you can extend it, such that U restricted to this set K represents a preference ordering. So this condition gives a complete characterization in the finite case. And now the proof. The proof by Richter and Wong, the only if is, of course, immediate. The only if part is immediate. If there is a concave function representing the preference ordering, then you can have either A or B. You cannot have any other thing. Then, how do you prove that it's sufficient? This follows by duality, and this is how Richter and Wong did it, and I will spend a few minutes and explain to you what the duality argument is. Now, what happens? What blocks the light? Ah. The lights come from here, so here it's reflected. Very sophisticated. So here you have the proof. So K is this set x1 up to xn, and you have a preference satisfying condition G. Then, for a concave utility function to represent preference ordering, it suffices, but it's also necessary, to find real numbers, which will be the utility levels, ui. So ui is the utility level at xi. And since it should be monotone, if xi is better than xj, then ui should be minus uj should be positive. And you should have super gradients, really. ui prime vectors. You cannot see, okay, you cannot see that this is bold, but this is bold. Don't you see that this is bold? This is boldface. So this ui minus ij minus gradient times the distance should be greater than or equal to 0. And if they are indifferent, you should have equality. So you have here a system of linear inequalities. It turned out that the theorem of the alternative of the every duality theorem that you can think of, actually, would show to you that the solvability of this linear system is equivalent to the condition G. So that duality gives you that this is, and then once you have this, you have concavity. If you have concavity, you have this, and this is equivalent. Okay. So what I was, after Richter showed me this, I started to think, well, I was a bit disappointed because I wanted very much to have this, well, at least these conditions and this picture that I showed to you. I thought that it should work in this case as well. And maybe even something which this one. And indeed, it does. So in our first method, we'll compute only the candidate values and not the derivatives. You see here, this is perhaps one of, I see two drawbacks to the Richter-Wong method. One drawback is that you at once, there is sort of an overkill. You are really interested only in the UIs, which are the utility levels, but instead you compute not only the values, but you compute also derivatives. They are important economically, these derivatives. They are priceless, but they are not what you ask for. Secondly, when you use a linear programming method, a duality method, then this is an iterative method, and the iterative method will converge. However, you get all variables at once. It is not that you can get some variables first and some variables later. Whereas here, suppose you have 100 difference in difference levels, and I'm interested in utility values of the 30th one. I'm not so much interested in what happens in the very high levels of utilities. Here, you have to compute everything in order to and you don't see the geometry. The set K, the indifference relation, you don't see them anymore when you do duality. And I would like to see the set itself and the reference itself. So what should we do? So we denote the finitely many indifference classes by L1 up to Lm. And now we use a sort of a, perhaps I will explain the idea. The idea is that the construction is inductive. We go from the bottom, like we did in this infinite case, we go from the bottom up. Okay, we go from the bottom up. So first of all, we assign the value 0, if you wish, to the lowest utility level. But then I have to be careful already for, then I assign the level 1 for the next one. But then already for the third one, I have to be a bit careful. Why do I have to be a bit careful? Because I want that inequalities of this type should always be satisfied. And these inequalities go. In the induction, you have, in the first step, or in the second step, I assign the value 1, or let us say 0 for all the bottom, and the value 1 for everything above it. But then if I assign 1 to everything above it, how do I know that I will have enough spare room when the things will, in the next stages, I will get their points which are preferred to what was in step 2. If you look at this picture, you see the problem. This point here, C2, is on one hand is a convex combination of points which are worse, and then monotonicity is all you need. But it is also convex combination of things which are better, and maybe even much better. And still I want that the value here will be bigger than the convex combination of what you have here. And how do you know that you can do this? So for this, you need the induction. This is the main induction step. So here is a proposition. So I define preference K, which is only for the sake of this proof. The case preference is that one that it is like the original one for the first K levels, and then everything else is indifferent. And then the proposition is the following. There exist three numbers, u1 up to um, such that for every k, the function which is defined by uk x equal to uj for x lj less than k minus 1, and uk for all those which are better, is a concave utility function, and you have room to spare. So Cj is defined as a set of all points such that x is a strict convex combination of points for which you have probability b, which means that x is strictly better than 1, so it is also strictly worse than something else. And then I assume that I have this strict inequality still. So this strict inequality means that I will be able at the next steps or at later steps, I will be able to enlarge some of these and still have this here an inequality. This is something which has no analog in the finite case. And then once you do this, the induction is quite simple, and the proof of this is also quite simple. So this is one construction. Another construction is slightly different. I want to construct actually also the vectors. So the first stage is that I construct with every point, I attach a direction. You see, this is the same picture as was before. The m's are the convex hull of this indifferent sets. And since these are convex sets at every boundary point of a convex set, you have a normal vector. So I pick a normal vector. This is this proposition 2. For every x in K, there exists a vector P, such that P inner product y minus x is greater than 0 for every y which is preferred or indifferent, but it's strictly positive if y is strictly preferred to x. This needs, you have to prove that it's followed from G, but you can prove it. So you have let us say, unit vector, which you call P of x. Now comes the second problem. We would like to attach lengths to these vectors. We have directions, but we don't have lengths. In order to, if you have a gradient of a function, the gradient has not only direction, the gradient has also length. So we have to assign lengths. In this business, which I did not explain to you, the main point is to assign lengths. Assigning directions, they come from the geometry, but the lengths are the one which you have to work hard to assign in a consistent way. So here also we want to assign lengths. Now ideally we would like to assign only lengths. This apparently cannot be done, but you can assign at once both lengths and utility levels, as the following proposition says. Yes, there is here, I remember here something about expenditure configuration. This is another, so these vectors can be interpreted as prices which tell you that if you choose a point, you choose a normal to the indifferent surface, then this would be the price at which such a point is attained. So that in, if you wish, empirical research, you have really pairs of prices and consumption both. So these are the basic ingredients of any empirical theory or behavioral theory. Then I don't want to talk about this now. Maybe I'll talk later about this. So now the proposition is the following. There exist positive numbers lambda I ui such that ui is strictly less than uj if you are at a lower level set, and we have that uj always, no matter whether j is greater than I or whether j is less or equal to I, you have the inequality 3 holds. So this lambda I serves as a lambda I times p is a subgradient or supergradient for this convex function. Now this is very similar to the system of inequalities that Richter and Wong constructed. However, the important thing here is that once again, the ui's and the lambda I are computed step by step. It is true that I cannot compute the ui's alone, but I compute them from the bottom up, once again. So this is related to the Afraid construction. I think I will skip this now. And instead, I will come to another mathematical question, and this is a question of least concave utility functions in the finite case. Okay. Recall that a utility function v representing a preference ordering on a space X is least concave if every concave utility function representing it, the same preference ordering on X, there exists a real concave function f such that f is strictly increasing and u equal to f of v. So this is you can really induce relation on the set of all concave functions which represent a given preference ordering. You can say that a function can be more concave or less concave. For example, if you take the ordering, the natural ordering of the real numbers, the least concave utility function is just a linear function. And then every concave function is more concave. But then you can have more concave function and an even more concave function. An individual may be risk neutral if the function is linear. It can be more risk averse, and it can be much more risk averse. Okay, so this is a natural, and the least concave utility functions are a natural construct. If I have time, I will perhaps explain a bit more about where they appear in applications. But even mathematically,
they wouldn't be strictly concave,
right? It depends on the preference ordering. They might or might not. No, the theorem. The only theorem that the answer is no. The only theorem that I have is the following: that if you have a compact set, okay, the underlying preference ordering is C2 or C3 or something like this. Then in every indifference surface, there is one point where the second derivative, where they are indeed not strictly concave. But it may be that your geometry may be such that you have on every preference ordering at most of the points, the thing is strictly concave. Okay? This can happen. The theorem is that it doesn't happen at every point. That actually at every indifferent surface, you have one point where this doesn't happen. So it is least concave in the sense that you are saying that it is not strictly concave at least one point in every preference ordering. But once again, this follows from compactness. Because if you have non-compact set, then it may be that the curvature will tends to 0 at infinity, but will be still positive at every point. Okay? Nevertheless, so now I want to show you by means of it. So, okay, maybe I will start by this one. Least concave utility functions are cardinal. Cardinality means that they are, usually utility functions are defined up to transformations. If you take a monotone function transformation of a utility function, it's a utility function. Cardinal utility means that up to multiplication by a constant and translation, it is unique. This is called cardinal utility function. These are the von Neumann-Morgenstern cardinal utility functions. So least concave utility functions are cardinal, very easy to see. And they play a role in risk analysis, as I said very quickly, also in confrontations. In confrontations, it turned out, maybe you would like this, if I and you are trying to bargain, then I would try to pretend as much as possible that I am as least concave as possible, compatible with my known preference ordering, because this makes my negotiation power stronger.
Why does it make power stronger?
Because in order to enhance my my utility, you have to give me a lot more. There is a model. What I'm saying is a theorem. I can write what I call the Nash squared game. You have a game where you and I have to agree on partitioning something, and we both know what our preference orderings are, but I don't know what your utility functions are. And then it turns out that this makes it to a zero-sum game, sort of, and the optimum for me is to assume that that my utility function is least concave. So there are other reasons why least concave utility functions appear also in behavior, not just in mathematics. So example 1 appears as if things are all right. Let X be a finite subset of the unit interval. Then there exists least concave utility functions representing the natural order on X, and they're all given by U of X equal to alpha X plus B, with alpha positive. So this is very good. However, examples 2 and 3 are going to show to you, in most, well, I don't want to say most because I didn't give a measure on it. In great many finite cases, you cannot have least concave utility function. You cannot have even minimal utility function with respect to set. And let me show perhaps a picture. So this is, for example, number 2. So I have here 3 points. 0, 0 is worse than 0.5, 0.5, which is worse than 0, 1. Okay? Now, all utility functions, which will represent these ordering, will be of the type beta x1 plus x2 for beta between -1 and 1. And U beta 1 is more concave than U beta 2 if and only if beta 1 is greater than or equal to beta 2. But then you see that if you look at this picture, you see that the point 0, 1 plus beta over 2 will be indifferent to 1/2, 1/2. So where this point is depends on what beta is. So all these betas, for all these different betas, these things are not even comparable because they give you different preference ordering. So not only you don't have least concave because -1 is out of the picture, but these are even incomparable because they give you different preference ordering. And you may ask, well, this is because we have here an extreme point, The second example shows you that you don't have an extreme point for this. If you look at, here you have 0, 0, 0.5, 0, and 1, 0, 0.5, 0.5, 0, 1, and these are equivalent. This is better, this is better, this is better. Then you can show that, once again, it is alpha times x1 plus x2, and indeed, you don't get, and they are incomparable. So, in a strong sense, you don't have functions minimenta convexa in this case. And so let us, the question is, yeah.
So let's sort of think that there's a problem with
The answer is the same question was asked by the referee when I wrote the first draft of this paper, and the answer is, I am quite positive that I have some strong suspicions who this referee, hostile referee was, and it was, and I don't think it was you. But this is a natural question. The answer is very implicit. You can write. What happens is that you can have write very implicitly conditions that will guarantee convergence of a utility function here. You can write a sort of a uniform, quote-unquote, G condition, and you get convergence. However, what I want to explain, and this I have in my last slide, why you don't have, in the finite case, least convexity. Why you have this only in the infinite case. And the reason is, the reason is that if K is a finite subset, the methods that I used, so like taking suprema here, or taking infima, all this would not work in the finite case. Because in the finite case, we had always strict inequalities. You want ui minus uj to be strictly positive. And this you lose if you go to infima. In the continuous case, if you look at these limits, well, not in this bad case, but if you are in the good case where this is the limit, then you still have strong inequality between this point and this point, which you don't have in the finite case. So this means that the concept of least so the construction doesn't work. Secondly, here, in this construction, I do the most efficient thing. In the construction that I showed to you, I don't do the most efficient thing. There was always, as I explained in the method, there was a leeway. I said I construct the first step and the second step in such a way that there will be still room for the next stages. So there is no most efficient. There was a strict inequality. There was no most efficient way. So this explained why the thing would converge, but would converge at each of the steps you don't have this. And there is one more point that I want to make concerning the least concavity. Least concavity is a second-order concept. Now I mean second order in the logic sense. If to say that a function is least concave, really, you say for this function is minimal among all functions. So this is not in the if you look at it is not only it is not in the calculus of proposition, but it is not even in the predicate calculus. You cannot explain this as a first order predicate. It is really a second order predicate because you quantify a function which is minimal amongst a set of functions. So whereas in the finite case, you can get probably only elementary concepts if you say you quantify only over sets. And this is probably the deep meaning why you cannot have, in a natural way, least concavity function for finite sets. And as I hinted before, there are non-standard least concavity functions, but they play a different role in places which are not concavifiable. Now, since this is Microsoft, I have to say, and since Uri Feige is here, I have to thank Uri because one of the questions that this hostile referee asked was, how about computability? To compare my method with this of Richter and Wong. And so I went to local experts, and Uri referred me to the book by Lovash on where there are lots about computability of convex, the question finding supporting hyperplane, is this computable in what sense, and so on and so forth. So I convinced myself, and maybe I am wrong, but at least the referee didn't say that I am wrong, so that's the important thing, huh? So I convinced myself that the method of Richter and Wong is efficient from the computational point of view, because it works in a polynomial time. Superficially, it would appear that my method will need more time, but one can arrange it in such a way that the two methods that I suggested will also work in polynomial time, so that while my methods are not better computationally, they are not worse, and they have, as I said, the advantage that you see the geometry and you can work, you build the thing from the bottom up, so you can stop if you wish. Okay, I think this is a good point to stop. Thank you.
I have a question about the crash core.
Yes?
Will there be a check? No.
Okay, there will be a test in Rehovot, not next week, the week later.
Okay. No. So, starting at the from the beginning, the assumption of having such an order is very natural, and then it seems that there's sort of a jump of faith to assume that there's a utility function. Now, my question is, can you start with assuming that you have this order on K, and then extend it to not only an order on K, but an order on lotteries in which you sample from K. So, like, do you prefer to get with 50% this item and with 50% that, or some other lottery? If you start with such a preference on samples from K, can you then, does this define anything?
Okay, this is a very good question, which has been posed and answered by von Neumann and Morgenstern. What you describe is precisely the so-called von Neumann-Morgenstern utility theory. So perhaps let me make a short historical statement. Utility theory was introduced in the 19th century by the great classicists Ricardo, Marshall, and these people, and they did not associate it with risk at all. Then, in the 30s, Paul Samuelson essentially said, well, all this utility business is nonsense. It is only the underlying preference ordering. The utility functions, since they are not uniquely determined, they cannot give you any more insight. Then von Neumann and Morgenstern rescued, quote unquote, utility theory by defining the preference, the basic space on which you define the preference relation is a space of lotteries, what you call the space of samples, a space of lotteries. And on the space of lotteries, they proved the existence, under certain assumptions, the proof of the existence of a utility function representing these lotteries. Now, this was one of the points that I cheated. I regarded already this utility on the space of the commodities as being derived from a von Neumann-Morgenstern utility on the lotteries of the space of commodities. So when I drew this infamous picture which I showed you about this investor or person who buys insurance, if you're at risk loving or risk averse, there is already the underlying space on which there is a preference ordering is really the space of lotteries. So, for example, when you buy a lottery ticket, this means that you prefer getting a huge sum in small probability for certainty losing something which is bigger. And if you buy insurance, this means that you prefer the certainty of paying the premium over the uncertainty of losing a used time with lower probability. So there is, what you are saying is exactly von Neumann, except for the axioms and which
Right. There should be some axioms.
there should be, and there are some axioms there, and then of course people started, because von Neumann motion have a unique utility function, so people said, okay, these axioms are not natural, and there has been big industry, including, but not limited to, the late Amos Tversky and Kahneman, and their experiments, and also the Allais paradox. So there is people made quite a nice living out of this question during the past 50, 60 years. Okay. Have a nice